Welcome. This technology addresses a long-standing limitation in conventional devices. Let's examine how it works and why it represents a meaningful step forward. I will use a text-to-speech application to provide a clear and easy-to-understand explanation. The demand for AI-oriented servers is rapidly increasing, and with it, the power consumption of the semiconductor devices they rely on. The heat generated by these devices, along with the cooling systems required to manage that heat, is growing at a pace far beyond anything seen in the past. As a result, there is a strong need for semiconductor devices that can operate at high speed while consuming far less power. However, the gate-all-around GAA and nanosheet transistors currently in use or under development do not fundamentally solve these challenges. Optical interconnect technology has emerged as a promising alternative capable of surpassing these limitations. Current proposals, however, focus mainly on chip-to-chip or board-to-board optical transmission. Ideally, optical transmission would also be implemented within the chip itself. Yet silicon is inherently inefficient as a light-emitting material, which has led to proposals that place external light-emitting devices either on or off the chip. This approach, however, requires additional optoelectronic conversion circuits, increasing both cost and data latency. As a solution, I introduce an on-chip optical transmission circuit, and a corresponding chip-to-chip optical interconnect, based on vacuum channel transistors that do not require external light-emitting devices. In this approach, electrons generated within the vacuum channel collide with a luminescent material, producing light that serves as the signal transmitted to the next transistor or to another chip. The vertical device structure figure 19 described in U.S. Patent 9,331,189 University of Pittsburgh operates at low voltages, around 2 V, because the source-drain gap is shorter than the electron mean free path. Electron transport is governed by Fowler-Nordheim field emission, and Coulombic repulsion in the accumulation or inversion layer is expected to lower the emission barrier at the cleaved edge. See Mittenji Kim et al. Ultraviolet enhanced photodetection in a graphene/CO2/C capacitor structure with a vacuum channel, J. APPL, Phys. 118. Figure 21 shows typical MOS transistor characteristics. The vertically stacked structure used in the experiment consists of 20 nanometers AL/30 nanometers SiO2/20 nanometers ITO/23 nanometers SiO2/PC substrate/20 nanometers AL, with a device area of 0.5 micrometers x 0.5 micrometers and an etch depth of 2 micrometers. Figure 1 shows an example of the vacuum channel transistor structure described in US 11-476-074 and US 12-062-650. These patents aim to reduce the gate leakage current and the source-to-substrate resistance found in the technology disclosed in US 9-331-189. Figure 2 and Figure 3 show examples of vacuum channel transistors used as photodetectors. In Figure 4, light enters the C/CO2 interface through the transparent ITO electrodes on the drain and gate. Under reverse bias, photogenerated electrons appear at the interface and produce a current in the transistor. In Figure 5, when light is incident on the interface between the gate electrode and the semiconductor substrate, electrons are generated under reverse bias, causing current to flow through the transistor. In U.S. Patent 9,331,189 from the University of Pittsburgh, Figure 35b discloses a light-emitting diode structure that includes a transparent conducting layer 122 and a phosphor layer 123. The phosphor layer emits light when excited by electrons. Figure 4 shows one example of a vacuum channel transistor designed to take an electrical signal as its input and produce an optical signal as its output. Figures 5 and 6 show additional versions of this type of device. Silicon normally does not emit light efficiently. However, by using a vacuum channel structure, light emission becomes possible. In this design, the gate-to-source voltage V_GS controls whether electrons are emitted into the vacuum channel. Meanwhile, the drain-to-source voltage V_DS determines how much energy those electrons have when they strike the phosphor layer. Because of this, both whether light is emitted and how bright the emitted light is can be precisely controlled by adjusting V_GS and V_DS. The light-emitting structure shown in Figure 5 can be used in displays, such as those in mobile phones or televisions. In this approach, each pixel of the display can be created using this type of light-emitting device. The fluorescent electrode can be made entirely from a conductive material that produces light when hit by electrons. Examples of such electronic-sided phosphor materials include GaN with added aluminum compounds, ZnO, Zn, Senior TO3, PR3+, and Senior In2O4, PR3+ with added aluminum and yttrium. These materials can be excited by relatively low electron beam voltages, typically around 10 V or less. Figure 7 shows an optical transmission circuit using a vacuum channel transistor. If the second transistor uses a conductive electrode like aluminum instead of a fluorescent one, it operates as an optical input, electrical output device. Figures 8 and 9 show an interlayer PCB transmission circuit using a light-emitting vacuum channel transistor. The photosensor can be a simple reverse-biased p-n junction. Compared with TSVs, this optical method removes the need for physical vias and enables faster, simpler signal transmission. For high-speed signal transmission, silicon photonics is being developed as a way to use light instead of electrical signals. However, because silicon cannot emit light efficiently, co-package optics has emerged as an alternative approach. In this method, an optical transceiver, responsible for converting light to electrical signals, is mounted directly on the server's printed circuit board. This technology integrates optical components such as waveguides, modulators, photodiodes, and 3V lasers on a silicon substrate. As a result, it faces challenges related to cost, power consumption, and heat generation. Silicon photonics is mainly used for chip-to-chip or board-to-board communication, and very little progress has been made in optical transmission within a chip, especially for large-scale integrated circuits like LSIs. The technology introduced here enables optical transmission both within a chip and between chips. It does not require external light sources or optical modulators, and it can be manufactured using existing CMOS production lines. It also inherits the advantages of vacuum channel transistors, high speed and low heat generation. In addition, the structure is simple, making it low cost and suitable for further miniaturization. This technology is covered by the following patents. JPB 0068189131. JPB 0070397763. US 11476074. US 12062650. TW 18088903. CN 1135068824B. Currently, this technology is at the idea level, but I am looking for institutions and companies that will evaluate and adopt it. Thank you for watching. I would also appreciate it if you could take a look at the uploaded low voltage and CMOS compatible vacuum channel transistor.